Alright, so today we're going to take a look at section 9.1. We're going to talk about how probabilities are determined. A little bit of what we're going to do today is going to look familiar if you've taken contemporary math. If you haven't, that's okay too. But you may see some similar things to what you've seen in that classroom before. So to start with a few sort of definitional things. An experiment is simply an activity whose results can be observed and recorded. So an experiment could be, we took a test. An experiment could be, I counted the number of something, jelly beans that were red in the bag or something like that. So it can go from like science experiment, real formal, to something very simple, just like counting the number of jelly beans in the bag, okay? An outcome is a possible event, or a possible result of an experiment. So it's a possible something that happens. So you get the bag of jelly beans, it's possible that there's a black one in there. And if there is, I throw a black one. Okay, so that's a possible event or an outcome. A sample space is a collection of all of the different outcomes. So if you were talking about, say, a bag of M&Ms, and you were to list out all the colors in a bag of M&Ms, and if you listed out all of the colors, that would be the sample space, because it would include all possibilities. And then an event is a subset of the sample space. So it could be a single outcome, right, like pulling a red M&M out of the bag, or it could be a combination of things, like, for instance, what's the possibility that I pull out a red or a yellow? Okay, so two different outcomes pulled out at the same time as a possibility. All right. The law of large numbers, or Bernoulli's theorem, says that if an event is repeated a large number of times, the probability will reach a fixed number. So to give you an idea of the way that that's talking about, is that if you were talking about over a large span of time, how many or what percentage or what probability is it that you have a boy versus a girl? If you were pregnant, you're a boy versus a girl. It should be a 50-50 chance, right? You all know the families though that had 6 girls or something like that, right? A boy, 6 girls, you start to wonder what's going on with that. Okay, so, but if you repeat the outcomes a large number of times, and large would be more than 6, it should be 50-50, right? So that's what this is talking about, is over a large number of times. Okay, another example is, for instance, we'll do a die. If you roll a die a large number of times, maybe 10,000 times, 100,000 times, about 1/6 of the times it should come up with the number 3, right? Okay, that doesn't mean that every individual roll will automatically, so it doesn't mean if I roll it 6 times, one of them is going to be a 3, right? It means a large number of times we're going to approach a fixed value. Probability is determined in this way. The probability event is the number of ways the event occurs or can occur over the number in the sample space. So this is the number of elements in the event divided by the number of elements in the sample space. So, so let me go back to my die example. So you roll the die, right? And let's say you want to know the probability that you'll roll an even. So how many ways could you roll that die and get an even? What could you get and satisfy that condition? A 4? Or 2? Or a 6? Right? So how many different ways could you get an even? 3 ways. How many different things could you get if you roll that standard die? 6 different options, right? So 3 would be on top. It's the number of elements in the event being I rolled an even, divided by the number of ways that I could roll the dice period, die period, which would be 6. So that's what this is looking at, okay? So if you were talking about the M&Ms and you in advance counted the M&Ms or whatever, you looked at the M&M bag already, so it's not opaque, that is, you can actually see inside of it. So if you're looking at this and you know that there are 5 reds, and your event, your event you're talking about here is the probability of getting red, you put that 5 on top, and then you know that there's 32 M&Ms in the bag, and 32 would go on the bottom. That's the way we get the probability. Mutually exclusive events are events that have nothing in common. And we've seen this notation. You may or may not have seen it, but this notation comes up both in contemporary math and in math 1. And this is an intersection. It means what they have in common. And if they have nothing in common, we say that that's the empty set, and that's the notation for empty set. So it flat out means they have nothing in common. For example, if I only draw one M&M out of the bag, unless there was something wrong with the manufacturer of the M&Ms, it's either red or it's yellow, and it can't be both. Make sense? So if I have the event, drawing a red and drawing a yellow, those are mutually exclusive events. They have nothing in common. You can't satisfy both at the same time. However, if I draw two M&Ms, could I satisfy both at the same time? Sure could. I could draw one red and one yellow. So if the event was the issue of drawing two M&Ms, then those would not be mutually exclusive possibilities anymore. Are you with me? Okay. All right. Let's see what else we're going to look at. All right. For any event or any outcome, the probability of that outcome is between 0 and 1. And probabilities are actually just decimals, kind of like they correspond to a percent, okay? So if you think about this, right, what is the likelihood or the percentage chance that something happens? Well, it either never happens, that's 0% chance, or it always happens, that's 100% chance. That's what these probabilities are as well. A 0 probability is the likelihood that it will flat out not happen. It's not going to snow today. 0% chance, right? Okay, but what's that? Okay, Dr. All right, and then the flip side of that is 100% chance that something's going to happen today, right? So with the exception of Jesus returning, it's going to turn dark tonight. 100% chance. Happens every day, right? Maybe not in Alaska or the North Pole, but here it does in Oklahoma. So here's an example. So this is theorem number 9 says the probability of an event is equal to the sum of the probabilities making up disjointed events or mutually exclusive events. So again, take my example where we were doing the rolling the even on a die, okay? So one way to roll the die, and we want to talk about, so let's say the likelihood of getting a 2. The likelihood of getting a 2, the probability of getting a 2 is what? How many ways can you get a 2? 1. If you just roll it one time, you can get it one way. 2. Out of how many ways total? 6. How many ways can you get a 4? 1 out of 6. And how many ways can you get a 6? 1 out of 6. Because getting a 2 or a 4 or a 6, those are mutually exclusive or disjoint events. So if I want to figure out the likelihood of rolling an even, I can add the 1 6 plus 1 6 plus 1 6, and it equals 3 6, which was 1/2, which is exactly what we got when we simply counted the number of ways of getting even and dividing by 6, right? So if the events are disjoint or mutually exclusive, then we can do it from either perspective and it will work out the same way. All right, if A and B are mutually exclusive, then this is actually what we said, but in symbols now. The probability of the event A union B, that means A or B happening, rolling the 2 or the 4, is equal to the probability of rolling the 2. Okay, I didn't really mean to write a 2. The probability of rolling a 2 is the probability of A plus the probability of B. But this only works if they're mutually exclusive. Okay? So for instance, when I talk about event A being rolling an even and event B being rolling a prime number, those are not mutually exclusive. Why? Because 2 is true. Because 2 is prime. 2 is both even and it's prime. So the events rolling a prime and rolling an even could both happen at exactly the same time. They're not mutually exclusive. So if I have that situation, this probability formula will not work. This will only work if A and B are mutually exclusive, have nothing in common kind of events. All right, theorem 9.5 is a relationship somewhat like 9.4. It's another formula. So if I have the probability of event A, let's see if you guys remember what this notation means for Math 1, for those of you who've had Math 1. Do you remember what the A with the hat on it is? It means everything not in A. You may have also heard the word complement. There's other notations for that. There's a notation where you put a prime on it, kind of like, you know, the apostrophe at the end of something. That's another notation you'll sometimes see. Another notation, again, it's not one that's in our books, but another notation you'll sometimes see is the little C, like as a superscript, you know, like an exponent that says C for A complement. But they all mean the same thing. They just mean the things that are not in A. So if I talk about All right. So if you're talking about the probability of an event happening, plus the probability the event doesn't happen, well, there's a 100% chance one of the two is going to happen, right? Either it rains or it doesn't rain. Right? Sometimes I give you an example. You're either pregnant or you're not pregnant. There's no third option, right? Okay. Same thing. It's either this or it's that. It's one or the other situation happening. So it's either true or it's false. It's not sort of maybe sometimes true or false. Okay. And there's lots of ways we could write this formula that are equivalent to this. So we could say that the probability of event A is 1 minus the probability of the complement. Or we could say that the probability of the complement of A is 1 minus the probability of event A. And in reality, all I've done is a little bit of algebra, right? I've added or subtracted something from the side. There's nothing really different about any of those formulas. But let me write this down too, in case you guys didn't think it was important. And we look back later and say, what the heck was that? A bar is the complement, which is not spelled like, hey, nice shoes, okay? Complement with an E in the middle, complement of event A. Okay, got yourself a note if you don't remember what complement is or haven't seen this before. This means everything's not in A. All right, so I've actually done several different sort of properties of probabilities, and we're going to combine them all onto one slide so that we've got a place where we can look back, in particular when you're doing your notes or not your notes, your homework or whatever, and you can say, what were all those properties again? So we're going to put them all together here. All right, so one property that I said but never wrote down is the property, or the probability rather, of the empty set is 0. This is an impossible event. The probability it's going to snow outside today. I'm not a weatherman, but I'm pretty sure it's 0. I'm looking outside, it's awfully sunny out there. I'm pretty sure it's not going to snow. Okay? The probability of the sample space, that is any possible event in the sample space happening, would be 1. Something's going to happen, whatever the description is, and this would be called a certain event. Okay, so the probability that it will at some point be dark outside today is 100% chance. It's probably a good one. All right, the next one I actually have written down. It was on a previous slide, or I didn't write it, it was typed. It says the following. It says the probability, it's not supposed to be an S in the letter, it's supposed to be an A, I'm sorry. The probability of any individual event happening is between 0 and 1. It either never happens, probability 0, or it always happens, probability 1, or it's somewhere in between. Right? So when we look outside, or when we watch the weather and they talk about a % chance for rain, you take the percent, turn it back into a decimal, that's the probability of it raining today. Okay? So this is for any event A. The next one I've also written down, if A intersect B is the empty set, that means that they have nothing in common, then the probability of event A union B is the probability of event A plus the probability of event B. So that's my example of the probability of rolling a 3 and the probability of rolling a 5, or whatever on the die. Both happening at the same time, so we can just add the individual probabilities, and that would be exactly the same as rolling a 3 or a 5. All right, this next one I haven't written down. So if we're talking in general about the union, probability of the union, and we don't know if they have anything in common. Okay, so this is my primes and even numbers example. Primes and even numbers, they do happen to have something in common, which means, equation number 4 is not going to work. What then? Well, you can still take the probability of one event plus the probability of another event happening. The problem, if you will, is that you will have double counted the number 2, because the number 2 is both prime and even, right? Which means I counted it when I counted the prime numbers, and I counted it when I counted the even numbers. So what I have to do is I have to remove my double counting. And so this probability is removing the overlap. It removes what they have in common. One time. Okay, so let's do numbers. Let's imagine. We're not gonna spend too much here, but imagine we've got my die, right? We've already done the evens. We know there's 3 evens. How many prime numbers are there between 1 and 6? Tell me what one of them is. We know 2 because I already said 2. 2 is prime. What else is prime? 3 is prime. And 5 is prime. Reduction 3 prime numbers. 6 and 4 aren't because they are each 2 times something, right? And 1 is neither prime nor composite. It doesn't classify as either one. Okay. So I have 3 evens and I have 3 primes. And that does not make 6 because I counted 2 twice, didn't I? It's a problem, right? Because if I said there's 6 out of 6, that would mean 100% of the time I get either an even or a prime, and that's not true. Sometimes I'm going to roll a 1, and it's neither even nor prime. Is everybody with me on that? So if I were to count the 3 items here for evens, and then the 3 items here for primes, I would have to remove 1 because I counted the number 2 twice. I counted it in both of those descriptions. So if I take my 3 plus my 3 and then minus the 1, I end up getting 5 of them. Because it really is everything with the number 1, right? So 5 out of 6 times I'm going to get a roll that's going to either be even or prime. Okay, so that's what this is describing. And this works for all sets A and B. And notice it actually works when they have nothing in common as well. So let's say I'm talking even versus odd. Okay, sets even, we roll the number things that are odd. They have nothing in common. So what's the likelihood I'm going to roll an even and an odd? This is audience participation time. What's the likelihood I'm going to roll an even and an odd? 0. It's an impossible event, right? I cannot roll the die and it be both even and odd that comes up. So what would happen is that this probability right here, in the case that it was something that can't happen, would be 0, right? So this equation still holds. It just sort of becomes a little bit odd to talk about it in that way because this is the number 0 at the end, which would and then turn into this case right here in number 4, wouldn't it? It would just end up being the first 2 things added because the last one was 0. All right, there's one more, and it's the last one that we did on the previous slide. Where did my last thing go? All right, the last one is that the probability of the complement is 1 minus the probability of the original event, or some variation thereof. I already wrote this one down 3 different ways, right? So it's the same thing down here, and this works for any event A.
Can you explain number 5? It's like your example. I don't see any dots here.
When I was giving you an example there of evens versus
Yeah, because
odds.
it says like 3 plus.
Right, so this over here says union, it means even or odd. This one over here says intersection, it means even and odd. So if I roll a die 1 time, it can be even and odd at the same time, right? So the likelihood, it would be like, you know, let me do it this way for you, Caleb. Let's do it this way. Let's say that event A is that I roll an even, and event B is that I roll an odd. So if I want the probability that I roll an even or an odd, or if I want the probability that I roll an even and an odd, which is, I think, the issue of what you're saying. You can let me know once I say it, okay? So if I roll a die, what is the probability that the roll, the number that comes up, is even and odd? 0. Can't happen. I can't roll the die and it comes up even and odd. So this right here is the word and. An intersection is what they have in common. And even and odd numbers have nothing in common. So the probability of that happening is 0. Over here though, okay, and I'm not going back to the formula per se, but this right here is saying what's the probability of rolling even or an odd. And what is the probability that I roll an even or an odd? That's, well, 6 out of 6. which is 1, right? There's 6 ways it can happen out of 6 ways total that you can roll. So this would be either 6 out of 6 or 1. It is a certain event. It is for sure gonna happen.
I was just confused because you're like, what's the answer? And it's 0, and I thought you meant, like,
Just over here. I was just talking about over here.
0, and I was like, I don't see it.
Yeah, just the intersection.
So it's 0 is minus 0.
Exactly. You end up subtracting 0. Is that all right then? All right. So we're going to do an example of cards. So I always have some concern when I start talking about cards. They use cards in probability examples all the time. In fact, they use a lot of examples that you would see in a casino, and I'm not advocating you go there. Okay? To be very clear on the matter. This is not the point. However, there's lots of card games that perhaps you play with your friends, because we have decks of cards too that we can talk about. So, a few details about decks of cards so that everybody is sort of coming at this from the same standpoint of prior knowledge, because I know you're not necessarily. So, in a standard deck of cards, how many cards are there? There are 52. Half of them is how many? 26. There are 26 that are colored red and 26 are colored black. Okay, we're good. How many different suits of cards are there? There are 4 suits. What are they? Hearts and diamonds, which are both red, and then spades and clubs are both black. Okay. And how many of each suit is there then? There are 13 cards in each suit. All right, so thinking about our cards now. We have some cards that have pictures on them and some cards that don't, right? So tell me what kinds of cards we have. What are my number cards? What's the smallest number card? 2 is the smallest number card. What's the biggest number card? 10. So how many different number cards are there in a given suit? There are 9, because we go from 2 to 10, right? So there's 9 diamonds, and diamonds that are numbers, and there's 9 hearts that are numbers. Okay, are you with me? From 2 to 10. What else do we have besides the number cards? We have some face cards. So let's talk about face cards. What face cards do we have? King, Queen, and Jack. Okay, so there's 3 face cards in each suit, right? What am I missing? An ace. An ace is neither a face card nor a number card. Okay, and then there are some games, right, who will actually play that the ace is high or the ace is low, or if you play blackjack, you can use it either direction, actually. So it just depends, right? So we're not going to be worrying about what happens and who wins a deck of cards hand, but we're going to be counting the number of cards, but in a way that's acceptable, not in a counting cards way that gets kicked out of the casino, okay? All right, so taking a look at these, the first question we're going to ask is whether events are equally likely, okay? And in doing that, what I want you to do is that we're going to actually find out the probability of each event happening. That's what we're going to do to make that call. All right, so what is the probability that you get a face card? Well, the way we find probabilities is we write down the number of ways that you can get a face card divided by the number of ways that you can get any card. Okay, so how many ways can you get any card? 52, because there's 52 cards. So, and I'll show you a couple of ways to do this, but let me show you this one first. So 52, there's 52 different cards. How many of them are face cards? There are 12, right? You could reduce this. You don't actually have to. You can just leave it like this as well. But if you reduce this, it will actually equal what? About, I think it's 3 out of 13, right? Because there's 3 face cards in each suit, and there's 13 cards in each suit. So you could also do this by suit, and it would work. Does that make sense? Okay, so this is all about the face card right now. Now let's do not a face card. How many cards are not face cards? 40. We'll get to your 10 in a second, Chelsea. 40 out of how many? 52. And Chelsea told me 10 out of, what would it be? 13, which would be by suit, right? There's 10 cards in each suit that are not face cards. All right, so the question actually asks us, are these events, that is, getting a face card versus not getting a face card, equally likely to occur? No. How do you know?
Because they're
They're not what?
13 is bigger than
Because what?
10 over 13 is bigger.
Okay, so the probabilities we just found are not equal, right? One of them's larger than the other one. So because the probabilities we found are not equal, the events are not equally likely. So this one's no, or not equally likely. All right, so let's do clubs, hearts, spades, diamonds, all that next. Okay, so what is the likelihood or the probability that when you draw a card, it's a club? 1/4. And that's one way to do it. What's another way you could have done this? 13 over 52. And you can compare it in non-reduced form just as well as you can compare these in reduced form. So I don't care which one you do. Okay, so this is 1/4. What's the likelihood you get a diamond? Heart? And spade? Spade. So are they equally likely? That looks like a 9 than it was supposed to be. Yes, these events are equally likely. All right, what's the likelihood that you get a black card? 1/2, or 26 over 52. And the likelihood you get a red? Also the same, 1/2 or 26 over 52. So are these equally likely? Yep. All right, one more example. We're going to do these one at a time. There's several different things we're comparing on this. And what's the probability that you draw a king? Okay, so you can either say 4 out of 52, or what else could you do? 1 out of 13? What I heard? Yeah. All right, so if you think the 4 out of 52, it means you're counting there's 4 cards that are kings, that's 52 cards total. If you're thinking of 1 out of 13, it means you're thinking in terms of one in particular suit. So you're thinking about just spades, for instance. There's 1 spade that's a king out of 13 spades total. 1 out of 13. How about queen? Also a 1/13, right? Jack? 1/13. Ace? 1/13, and if the problem ended there, would they be equally likely? Yes. No, it doesn't end there. And then it talks about even cards. How many even cards are there in any particular suit? There are 5. 2, 4, 6, and 8, and then 10, right? So 5 out of 13. How about odd cards? That's 4 out of 13, right? There's actually only 4 odds. So are they equally likely? No, they're not equally likely. Is composed of 21 men, 34 women. There are 22 ed majors, 13 religion majors, 12 science majors, 3 math majors, and 5 English majors. Assuming no one has double major, which we need to do, otherwise the numbers are not going to work here. Okay, so it's an important thing to think about because you all know people who have double majors. So, assuming no double majors, if a single student is chosen at random, what is the probability the student is ... We've got some examples. So, what is the probability that the student is female? Out of how many? 55. Right? Okay, 34 out of 55. And we should look to make sure that this doesn't reduce, because if it does reduce, we should reduce it, right? Will it reduce? No, it won't. All right, how about a science major? 12 out of 55. Does that one reduce? No. How about an English or a religion major? Okay, so I want to draw your attention to something you did here and probably did it without thinking. The only reason you were able to do the problem right here, where you simply added the 5 and the 13 together, was because why? Okay, part of it's the word or, but there's something else.
They both have the same number. They both have a denominator of 55 to the right.
That's true. That's true. Something else though.
Because they don't overlap.
They don't overlap. They can't be both. The fact that you were told there's no double majors means that these possibly cannot, or these cannot possibly intersect. Right? This was, I don't know, property number 4 and 5, where we looked at those two different formulas. It said I can only add the two probabilities together if they had nothing in common. And we were told in this problem there are no double majors, so we know they have nothing in common. Does that make sense? Because you see, we could have done the problem differently. If this simply said a female or a religion major, you couldn't just add them together, right? Because if we added the female and the religion majors together, we would have double counted, or at least potentially double counted someone who happens to be both. Are you with me? Okay, we have one more. It says neither a math major nor a science major. There's at least 2 ways to do this problem. Okay, so Lauren, if you're giving me an example, you're giving me an answer, you need to tell me how you got it. Okay, so you added the majors up besides math and science, so tell me what numbers you added up.
13.
Okay, and then you wrote that number over the 55, right? What is that one? 40 over 55, which we would reduce, of course, later. But what is it? 8 over 11. All right. Did anybody else think of the problem differently? Because there is another way to do the problem.
I just added the math majors and science majors and subtracted.
Okay, so if you add the math and science majors together, so math plus science, math was 3, and science was 12, there's 15, right? And so what we've really done, and again, you probably weren't thinking of it quite like this, but you really found the probability that you did get a math for a science major, right? And then I know you said you subtracted it from 55 in essence, but what you've really done is you've done this, and then you found a common denominator, which is the 55. Okay? This actually, the reason I draw your attention to this is because it actually shows you that property number 6, where we did that complements idea, right? The number of ways something can happen is 1 minus the ways it doesn't happen. So we still get the 40 over the 55 here, which is 8/11. Okay, here we go. Yes?
But you are told you want to show all of them.
No, you don't have to. Now, that said, be real careful, right? Because if you give an answer where you accidentally added wrong or something, and I don't have anything to look back and see what the numbers were you added, to see that, oh, you just added wrong, you really knew the numbers you're supposed to add, you can't do anything with extra credit. So it's to your benefit to show something before you give me the final answer, but you wouldn't have to show a lot, or even, there's not a lot to show, and it depends on the problem as to how much you might want to show. The other thing, too, when you're taking a look is to think about, am I going to remember what I did when I look back at this after spring break? Because this test isn't happening, I don't think, until after spring break, right? So do you really want to wait 3 weeks and remember what you did 3 weeks ago to do the problem? So kind of give yourself some chance to remember by writing a little bit down to help yourself. Okay? All right. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the law of large numbers, the probability of tails, I can't talk, the probability of tails on the next toss is greater than the probability of heads. What is your reply? No, it isn't. So why?
Well, it doesn't say it changes like the probability of each, like it's still 50-50 chance, and it says that like it's a large, like 5 rolls.
Okay, so let me make the first comment you said is, first of all, something to the extent of each roll, let's say it this way, each roll is equally likely to occur. Another way that you can sort of think about, does occur have 2 R's in the end? I can't remember, okay. Another thing you could think about in this idea is that the roles are independent. There's no correlation between what happened the first and what happened the second time on the die, unless, you know, it does say it's a fair coin. Obviously, if the coin were weighted or something, that wouldn't be true. This is a fair coin. Then you said one other thing, Kayla. Do you remember what it was?
There's 5. There's like a coin is a large.
Yeah, I'm pretty sure that 5 is not a large number by any stretch of the imagination, right? So even so, if the student were correct about the one roll sort of, you know, happening on something else, 5 is not a large number. And this actually goes a lot back to the idea of what I mentioned earlier with children, right? Does anybody know people or family that has a large number of children and they're all one gender? You know, how many people? They have 5 boys. I actually know a family that has 6 girls. And then they started having grandkids. That is, the daughters started having children. And the first 4 granddaughters were girls, which were grandchildren were daughters too. So each time equally likely to be one or the other. So yeah, there's no one, the gender of one child does not affect the gender of the other. Very much like the rolling the head or flipping the heads or rolling a die or something like that. Each event is equally likely, doesn't matter what the event before it happened to be. All right, let's do this one. All right, the following spinner is spun 100 times. Joe claims the number 4 will occur most often because it has the greatest area on the spinner. What would you tell Joe about his conjecture? What is the probability that 4 will occur on any spin? And he says 1/4. Why? Yeah. All right, so let me change the problem slightly for those of you who didn't catch what happened. If he was throwing darts, would he be correct? Yes. If he were throwing darts at this and this were a target, he would be more likely to hit 4 than he would be hit anything else, right? But that's not what's happening here. He's spinning a spinner. And when we're spinning the spinner, it doesn't matter how much area it is, it matters what the angle was, all right? So now he's not correct. We'll say something like the issue is the angle the spinner goes through. And here, each angle, and you could actually say it's 90 degrees if you like, but each angle is equally likely, or each angle is, let's just say is equal. We'll do that. Each angle is equal. So the probability of the number 4, which we can write with this notation that we've been using, is actually 1/4, because there are 4 different areas on this diagram and they'll have the same angle that they're spinning through. Any question on that?